So for lesson 1 here, we're talking about the definitions of acids and bases. There's two main definitions we're going to keep coming back to. So there's the Arrhenius definition and the Bronsted-Lowry. They can kind of work together to help you figure out if something's an acid or a base, but they do technically mean different things. So an Arrhenius acid is a substance that dissolves in water to produce H ions, versus the base is a substance that dissolves to produce hydroxide. So like I'm looking here and I'm saying, okay, so I see this substance gives off an H. So therefore, I know that it's an acid. Okay, so go back up here. Okay, so I know it's an acid because it gives off this H right here, and that, according to the definition, gives off H. Okay, this one again, HNO3 gives off an H, so therefore these both are acids. I see that this gives off an OH, and this also gives off OH. So according to this definition, okay, that makes these both bases. The Bronsted-Lowry definition is a little different. Okay, that one deals with whether things take in hydrogen or give up hydrogen. So acid, it gives up the hydrogen, and there's 3 types of acids that we'll generally encounter. It depends on how many H's they have. So monoprotic means 1 H, so there's only 1 H here. Diprotic means 2, there's 2 H's. Triprotic means 3 H's. The base would be the thing that takes in the hydrogen. So I'm looking at this reaction here. I'm trying to figure out what's giving up the H, what's taking in the H. So I'm looking at the NH3 on the reactant side. It's NH4 on the product side. So that means that it gained an H. So the H2O gave up an H to the NH3. And that makes sense too, because I look at this and I'm saying H2O became OH, so it definitely gave over an H. So according to these definitions, the one that donated the H is the water. The one that took in the H is the base, which is the NH3. Looking at the next example, I have water and H2CO3. I find the water on the right. Well, now it's H3O+. And H2CO3 became HCO3. So I'm looking at it and saying, okay, one of these H's went to the water. So definition, again, this is the acid, that's the base, since this gave up the H to the other thing. Now we're going to look at some examples here of an acid-base just reaction in general to try to figure out what these things called the conjugate acid and conjugate base pairs are. So you're looking for the acid and then the base, and once you find that, the conjugate acid, okay, is how we're going to label it, Ca. That is the substance that results from the base gaining an H. Substance that results from the base gaining an H. Okay, so I'm looking at this and I'm trying to figure out again what's happening. Well, our water, H2O, became an H3O+. So I know that this gained an H from the NaOH. Okay, and that makes sense because it was NaOH, now it's just NaO. So using the definitions from before, since this gives up the H and this takes in the H, we would say that's the acid, that's the base. But the new thing is what's called the conjugate acid, and then the conjugate base, as you can imagine, is when it results from the acid losing the H, okay? So we're looking at this and we're saying, okay, so acid base, and then I'm tracking what's happening. So I want to pair them up in the way that you're probably already thinking about pairing them up, that these two things go together because it's basically the same compound with an H difference. These two go together because it's the same compound again with an H difference. Like the sodium needs to go with the sodium compound on the right. So I paired them up. The base always gets paired with an acid and an acid with a base. You don't pair up 2 acids or 2 bases because that doesn't make sense because there should have been an H transfer there. So the base gets paired up with what's called its conjugate acid, which is a substance that results from the base gaining an H. So base gained an H, so that's called the conjugate acid. This is called the conjugate base because this is when the acid lost the H. That's the substance that you end up with there. And look at the next one. I see KOH and HBr, HOH, ABr. Okay, so the K here doesn't really matter. You can kind of think about it without it. We're looking at the rest of the compounds though. The OH compound definitely goes with the OH compound here, okay? So we're pairing that up, and then the BR compound definitely gets paired up with the one that has BR over here as well. But I'm looking to see what happened to the H. So the H started off here, and if you see on the right, there's no longer an H with the BR. The OH was by itself, now it has an H again. So that H went from here to here. So using our definitions from earlier, that makes that the acid, this makes it the base. Then we're looking at their conjugate pairs. So that's the base. Its conjugate pair there is called the conjugate acid, which is the substance that results from the base gaining an H. This is the acid, so this is its conjugate base. Again, the substance that results when the acid loses the H. So acid lost the H. Now that's called a conjugate base. We're going to practice identifying these reactions as well as we work this unit. Let's talk about the difference between strong and weak. So strong acids and strong bases go through a complete ionization. So what that means is they all break down into their ions. So this is the acid, just a generic form for any acid. They generally start with H, so that's why it's written out as H, A standing for acid. What happens is we have the acid reacting with water, and the acid always gives up the H to the water. So we have H3O plus, and then the A is left by itself. The base reacts with water, okay, and the base takes in the H by the definitions we talked about before. But the big difference here is you'll see that there's a one-sided arrow showing everything breaks up into its ions. The weak acids and weak bases are different because they have very little ionization and they barely break up. So we have, again, a generic acid meaning a weak acid here, a base B meaning a weak base. But the big difference you'll see is this double-sided arrow. This double-sided arrow says a lot of it stays as it was with this arrow that goes backwards, meaning not a lot of it breaks up. When we practice writing these, what you're going to have to think about is how much should break up and show that with the arrows. So if I look through these examples, write the ionizations of the following acids and bases, I need to first recognize if they're an acid or base and if they're strong or weak. So I look at this table here and I'm saying, okay, strong acids are listed here. Notice they all pretty much start with H. Okay. The strong bases are listed, pretty much all have hydroxide at the end when you look down through all their formulas. Weak acids, there's a bunch of them listed here. This list could go on for a very long time, so this is just some of them. Water could act as a weak base. It could also act as a weak acid or a weak base, so it just depends on what it's reacting with. And these are the weak bases that you'll mainly encounter. But when we look at these, the strong acids is a pretty good list of them, strong bases, and so forth. But the other one that we're going to be looking at too, and we're just going to make a quick note, is magnesium hydroxide. That is a strong base as well. But the first thing we're doing with this table up here is we're looking through and we're saying, okay, so what are these? Are they weak or strong? So I see hydrochloric acid. I'm checking down through the list. I see it's right here, so it's a strong acid. That means I keep just the one-sided arrow, and I'm going to break it apart. So H plus and Cl minus. Sodium hydroxide right here is a strong base, so just the one-sided arrow is good. And then I have Na and OH. This one though, H3PO4, I'm looking to find it. It's right here. It's a weak acid. So what that means is it's just going to break up some. So I need to draw that arrow going backwards to show that I know it's weak and it doesn't really break up. Then I'll show that it gives up the one H and the rest stays together as is. Okay. The last thing that's on here is just a note about acids and bases. They're both very dangerous if they're especially concentrated or if you have long exposure to them. So these burns that are over here on the right, one's an acid burn, one's a base burn. So you can see that they're both as dangerous. It's not just that acids are dangerous and bases are not. We're never going to work with full concentrated, but you want to make sure that you keep in mind, even when you work with acids or bases, these are really severe, obviously, but if you get them on your skin, you definitely want to take some measures to wash them off so that way you don't have any